In this lab, we want to drive the 7-segment display using two counters, an up counter and down counter. The counters up are 8-bit counters, and we use the low nibble to drive the H0 7-segment display of the first counter, the most significant nibble of the first counter to drive the H1 7-segment display, the low significant nibble of the second of the down counters to drive the H2 7-segment display, and the high and the most significant nibble of the down counter to drive the H3 7-segment display. In order to control the two counters, we use the button 2 of the board, and we have to recognize the edge pushing the button to control the counters. So let's see the implementation of the counters. Up counter, the counters has input, clock and reset, a counter enable and the counter out. The asynchronous reset set the counter to 0, while each time the counter enable is equal to 1, the counter plus 1. Down counter is the same, but when the counter enable is 1, counter equal less than equal to counter minus 1. Let's see how to drive a 7-segment display. The bits are mapped 6 down to 0. 6 is G, 5, F is 5, E is 4, and so on, down to A that is equal to 0. The display is on when the input is 0. This is the FPGA pad. We have VCC on the one side of the 7-segment display. So to turn on a segment, we have to drive low this pin. In this case, we have an input from 3 down to 0, and this is the input, and for example, to drive 1, we have to turn on this one and this one. So we have to turn on B and C. So put 0 here and here. 0, 0. The other is 1. To turn on 3, we have to turn on this one, this one, this one, this one, and G. So we have 0, 0, 0, 0, A, B, C, D, and G, and so on. For 0, we have to put to 0 all A, B, C, D, E, F, but G. In this case, G is 1. So the 7-segment driver will be an entity with 4 inputs of 4 bits and 4 outputs of 7 bits. where the output is generated by the function called with input as argument. Let's understand the rising edge detector. So we need a pulse of 1 clock cycle in order to increment or decrement the counter. In this case, this is the wire connected to the button. And the button behavior is this one. In this case, we want a single pulse when the button goes down. Okay, so this is the input. This is the first stage of sampling, and this is the second stage of sampling. The output of the inverter is this one. So the pulse is 1 when this signal and this signal are high. So in this range we generate a pulse. And this is the VHDL implementation. R0, R1, and pulse. You should note that the output is the output of a flop. So here in the figure we have to draw a flop. And this is the output. To complete the 7-segment lab, you have to go into the folder RTL and complete the file where you find insert your code here. And you have to complete the down counter, up counter, rising edge detector, 7-segment driver, and the top level. Remember that you have to complete your exercise in order to implement such kind of top level. Then simulate your code and lay out your code on Altera Cyclone 3. Let's see briefly the architecture of the design. This is the top level where you have to instantiate heartbeat, down counter, up counter, and 7-segment driver. Of course, the rising edge detector. And you have to connect the 7-segment driver to the 7-segment LED, this one, and the input are up counter, for H0 and H1, and down counter for H2 and H3. And down counter for H2 and H3. Then let the blinking LED on dot point. This design is derived from the heartbeat, the previous heartbeat design, so we have the heartbeat here. And the button, the push button 2, that is the control of the rising edge detector. The output of the rising edge is the control for the counters. And let's see briefly. Counter down and 7-segment driver. You have to complete the code where you will find the insert your code here. Remember how to simulate a design? Start Model Sim and try to simulate, for example, we will simulate the rising edge detector. So change directory to lab 7 segment. We use solution, so change here and create library. Then compile rising edge detector. Okay, and simulate. Add wave star and fourth clock, for example 10 nanosecond. Fourth reset, starting low, and fourth input low. Okay, run for 100 nanosecond, and we see that we have reset low and clock. Now release the reset arrow, up arrow, 1, and run, for example, for 23 nanosecond. Okay, now generate an input pulse, 1, and run for 300 nanosecond. Oops. Nanosecond, and we see that input goes high, and this is the first strobe, second strobe, and here we have the output pulse. Now we can set input to low and run, for example, 200 nanosecond. The pulse is of 1 clock cycle. If we want to generate a script, select all the transcript, copy, and go to test bench. In this case, you can paste and delete all the comment. This is okay. Save and clear and run a script. Okay, and that's it. Now create the layout. So first thing to do is go to Solution and create new folder layout. Then new project wizard. Select the top level we want to layout, 7 segment solution. This is the top level. This is the, select the folder layout, open, and select the top level, RTL, and this is the top level. Add files, open, next, select the FPGA, next, next, finish, and now we have to set the pinout. At this point we can close the project, and remember you have to go to QSF file, open, go at the end and paste the pinout. Select all, copy and paste. OK. Close and open project again. OK. Start compiling. It's not present heartbeat, so we need to add the heartbeat files. We can add the heartbeat from the previous solution. Copy, paste, project, select the project, setting, and select the heartbeat. Add, OK, and restart compiling. Okay, let's check just for info. We didn't set clock, and this is the maximum frequency reached from Quartus 2 is 250 megahertz about. Now let's check the pinout if it is okay. Okay. Yes. User assignment, yes. Now let's check the design on the board. Turn on the board and start programmer. Okay. The board is programmed. As you can see, the previous design of the blinking heartbeat is already present, and switching the switch 9, the blinking LED is faster. Now, pushing the button 2, we have the 7 segment on the right that counts +1, and the 7 segment on the left that counts -1. On the button 0, there is connected the reset, so pushing the reset, we reset the board and the blinking LED stops.